Good morning. So today we're going to talk about the dot product and its applications. So this is yet another operation on vectors. This time not an intuitive one in the sense that not like the previous ones when the addition or scalar multiplication were pretty much intuitive the way they operated, right? So it was essentially multiplication or addition for each component. It is important to point out that all of these operations serve a purpose, many purposes, but the idea is that they are not invented just for the fun of it. I always want to start with at least one example, or shall I say a motivation for all of these operations, rather than just state the definition, because as much as possible, if the time allows, it's always better to know right from the beginning what the tool is good for, why do we bother, and why, especially why it is defined the way it is, because many of these operations, like I said before, are not really intuitive, especially the cross product. If I just start the way directly with the definition, it feels underwhelming somehow, or frustrating, because you want to know, why is it defined the way it is. For the dot product, we can actually have an example as a motivation for the operation, which is pretty easy to understand, from economics, for example. So let's say, for instance, a store has a list of products, and with the quantities represented by some variables. Let's say we're gonna have products quantity in pounds, let's say, and let's suppose we have three products. Let's say we have X apples, pounds of apples, Y I don't know, pears, and then Z plums. Let's squeeze it here, a third product, okay? And let's suppose that we have the unit price for each of these. So the dollars amount per pound. And let's say the apples cost $2 a pound. I don't know if the prices are real, but it doesn't matter, okay? So the pears are $3, and let's say the plums are, I don't know, $4 per pound. And we want to represent, let's say, a quantity which describes the total revenue. So I hope it's pretty easy to see how this goes. You're going to have to multiply for each product the quantity with the price per pound, right, per unit. So the revenue that comes from apples will be 2 times X. The revenue that comes from the pears is going to be 3, assuming we sell everything, right, is 3 times Y. And then the revenue that comes from selling the plums is 4 times Z. So this is essentially what I just showed you here, is essentially the dot product between the vector which represents the quantity and the vector that represents the unit price. So you can tell that, with this type of operations, you can formalize the data very quickly and very easily, right, for many purposes. So you can extend, of course, this to a much longer list. Is very amenable to implementation on computers and so on and so forth. But the mechanics, I hope, is pretty clear. What you basically do, you multiply each entry by entry, right, from both vectors, and add the two, add these products. Multiplication by entry and summation, and then the result is going to be a number, a scalar, right? So you take two vectors and you produce a scalar given by this summation. That's not the only use, of course, of the dot product. We'll get to more applications later, but for now, let's write down our formal definition for the dot product. And because it's different than the regular product, we're gonna emphasize with an actual big dot the notation for this operation. Although again, the context will be pretty clear, because it will take two vectors and will give you a scalar. So if I put two vectors with the multiplication sign between them, it's pretty obvious that I'm talking about the dot product and not the regular multiplication. So remember what I said before, the context matters, right? So suppose we have two vectors, u in the component form. From now on, we're going to use the component form. Let's say u is given by the the components x1, x2, x3, and then v, the components given by y1, y2, y3. Then the dot product u dot v is going to be x1, y1 plus x2, y2 plus x3, y3. So takes two, this is the dot product, right? So takes two vectors and returns a scalar, a real number. Remember what I said before, we're not going to always repeat the definition for R2, but whenever I don't do it, you should assume it's analogous, right? So in R2, again, if I have two vectors, let's say u of coordinates a1 and a2, v of coordinates b1, b2, it's pretty obvious that u dot v for two vectors in the planes is a1, b1 plus a2, b2. So that is the definition. And let's move on now with discussing some important properties of this operation before we move on to actual applications of the dot product. So first of all, there is a connection between the magnitude of a vector. Let's say, let me use a different notation here. So suppose u is equal to the vector given by ABC, like that. Let me think a little bit. I want a different, yeah, sorry about that. Let me actually use a different notation because I want to use C for something else. So so suppose my vector is now given by the coordinates a1, a2, a3. And let's talk about some properties. So there is a connection between the magnitude of a vector. Remember, the magnitude of a vector is square root of a1 squared plus a2 squared plus a3 squared and the dot product. Notice that I can write this summation of the squares that represents the magnitude under the radical as a dot product of the vector a1, a2, and 3 dot itself. So if you follow through with the definition of the dot product of the vector to itself, you're going to end up with a1 squared plus a2 squared plus a3 squared. Now if I square both sides, that means the magnitude of a vector to the power 2 is always the dot product between the vector and itself. That's a very nice property to keep in mind, which simplifies sometimes sometimes the computation, depending on the context. For those of you taking my class, remember you are allowed to have a formula sheet, so make sure that until you memorize these formulas, you can you extract all of these properties and have them in front of you. Some of them you'll use them so often that you'll memorize them anyway, but until that, make sure you have essentially like a formula sheet with all of these properties, because there's plenty of them for the whole class. So that's the connection between the magnitude and the dot product. As expected, the dot product inherits many properties of the regular product, including the distributivity. So for example, if you have three vectors, the dot product distributes itself to the summation of two vectors, vector summation. I forgot to mention something on the top here. Also, the dot product is commutative. I'm not going to prove all of these properties. Some of them are very easy to prove. Some others are a little bit more tedious to go through, although they're not that hard. So for example, the commutativity should be pretty easy to understand, right? I mean, if you look at the definition over here, I mean, it's pretty obvious that it doesn't matter if I say x1, y1 or y1, x1, right? So I mean, the dot product is commutative. and it is also distributive to the vector summation. Another important property which comes in handy, there is a commutativity between a scalar and the dot product. So that means if you have a scalar C, so let's say C is a scalar, and you do the scalar multiplication of the vector and then you dot the resulting vector with another one, you can actually interchange the scalar. You can commute the scalar with the two vectors. So all of these associations are true. Once again, it's very important to remember the context here, right? So in the parentheses, this is the scalar product. I usually, when I go over this in class, just to make sure that people are with me, I ask them how many operations do you see here actually. So maybe you may want to pause the video a little bit and ask yourself this question. In this last equality that I wrote here, how many operations do you see? And the correct answer is that there are 3 operations in total that you should see here, right? So here in the first parenthesis is the scalar product. This is the dot product. Scalar product here, and in the last equality, because this dot product gives you a scalar, so here in parentheses I have a scalar times another scalar, this is actually the regular product, the old-fashioned product from real numbers. So let's go over a quick example over the dot product and some of these properties. Let's say, for instance, I have a vector u of coordinates -2, 1/3, and v of coordinates 4 and 3. Then in this case, u dot v is going to be -2 times 4 plus 1/3 times 3. That's -8 plus 1, which is -7. Let's actually check the associativity that I talked about before. So suppose, for example, I want to do 3 scalar multiplication -1, 2 dot 1, 5. And let's check to see if it's equal to -1, 2 dot parenthesis scalar multiple 3 with 1, 5. Okay, so on the left side, let's see if I can squeeze it here. On the left side, the dot product will be -1 times 1 plus 2 times 5, which is 10, which should be equal to -1, 2 dot, let's do the scalar multiplication on the right here, that's 3 and 15. So now on the left side, it's 3 times 9, that gives me 27. And on the right hand side, -1 times 3, the dot product, plus 2 times 30, plus 2 times 15, I'm sorry, which is 30. 30 minus 3, that's 27 indeed. So that checks. I think I made a little bit of a mess here. I misaligned the page here a little bit. Sorry about that. I don't have actually a good eraser here. So you know what? Let me actually. Sorry about that. I misaligned the page. I'm writing actually on a regular page, and I don't wanna. Let me do it this last row one more time. I'm gonna put it here. So it was 3 minus 1 2 dot 1 5. I wrote without looking at the screen, so I didn't realize what I wrote here. So then 3.15, which is 315. And here's going to be 3 times -1 times 1 plus 2 times 5. And on the right, -1 times 3 plus 2 times 15. So anyway, take a moment and then check for yourself that the property works as intended, right? As it's supposed to. 10 minus 1, 9 times 3, 27. And on the right hand side, 27. All right. So let's move on to the second page, and then we're going to move on with some other properties related to the dot product. So we get now to some nice applications of these operations, and one of them is finding the angle between two vectors. This is very important applications And you'll see, I hope you're going to appreciate the value of these tools, because some of these, some of these applications make life much easier, in the sense that you could achieve the same objective without vectors, but it's far easier with vectors. And I hope we can show already in this section and the next one how efficient these tools can be. So why do you want to find the angle between vectors? Well, we'll get to an application immediately, but roughly speaking, that's important. For instance, if you want to know how forces, for instance, act on an object, you want to know, for instance, what's the optimal angle, or what's the effect of a certain angle between two forces that act on an object, and so on. I will also give many examples in this class. I want to warn you ahead of time from aviation, because I'm a little bit kind of a geek or passionate about this topic. So it's very handy to me to actually go over analogies or examples from aviation. And if you don't actually particularly like the topic, you might get a little bit bored, or you might think I'm obsessed with the topic itself. But it's such a handy field to come up with justification for what we learned in this class. So the angle between two vectors, right? So suppose we have two vectors. Remember, we can always have them starting at the same origin, because doesn't matter which representative you pick, and in this case, the origin, the initial point is the origin, and let's denote by theta the angle between them. So the goal is to find the angle between these vectors. So we're going to use actually a geometry property and then rewrite it in terms of vectors. So I'm going to actually come up with a new vector that forms a triangle with these two. Doesn't actually matter the direction, but let's say it's the vector that connects the terminal point of U as the initial point and the terminal point of V as the terminal point of this new vector. So if you look carefully, V is the sum between U and this new vector that I just came up with. Okay, so remember the vector addition, how it's defined. Use a different color here. So this one here plus this one here should give you V, right? The vector V. And that means this new vector that I just constructed here can be viewed as the difference between V and minus U. Or in other words, the vector sum, we didn't define the subtraction of two vectors, but basically that's essentially the addition between a vector and its opposite, right? So I hope it's pretty clear, because the reason why that's the case is because the sum of these two should be V, right? So U plus this new vector that I just constructed here should be equal to V. So in other words, U should cancel. Okay, so this new vector is the difference between V and U. Again, you have to be careful how you choose the direction, right? I mean, if I were to put the arrow in the opposite way, then instead of V minus U, I should have written U minus V. Okay, and let's now use a theorem from geometry, which is called the cosine law. That comes from geometry. You don't need to memorize it, which states that the magnitude of the side opposite to theta squared, so the magnitude of V minus U squared, is going to be the magnitude of the sum of the squares of the magnitudes of the other sides minus 2 times the magnitude of U, magnitude of V, and cosine theta, cosine of the angle between them. So this is the so-called law of cosines. It relates the sides of a triangle. It's from geometry, from classical geometry. It relates the sides of a triangle with the cosine of the angle between two of the sides. The only difference is that we refer to the magnitude of these sides by the magnitude of a vector. So let's try to simplify a little bit this quantity here, this equality. And remember, on the previous page, we mentioned that the magnitude of a vector to the power 2 is the vector dot itself. So all of these magnitudes to the power 2, I can rewrite them as the dot product between themselves. On the left, at least. On the right, I'm not going to do that because I won't need it. These guys will cancel, as you will see immediately. And let's do on the left side some distributivity and commutativity. Remember, we can distribute the dot product, so we can actually expand this just like we expand the multiplication of real numbers. V dot V minus V dot U minus U dot V plus U dot U. Remember, I don't take breaks, so I can keep the videos as short as possible. You should always pause the video to catch up with the computation. You can always have me shut up for a moment until you catch up. That's one of the advantages of this instruction way. So, moving on with the properties, in reverse, V dot V now is the magnitude of V squared. And because these are commutative, right, V dot U is the same as U dot V, I can rewrite it as minus 2 U dot V plus magnitude of U squared now these magnitudes cancel. We can divide by minus 2 both sides, so minus 2 cancels as well. And if you look carefully at what is left, we arrive to a neat, nice formula for the cosine of the angle between two vectors. U dot V over the magnitude of U times the magnitude of V. So that is basically the direct way of finding the angle between two vectors. And again, notice the beauty of it is that now if you just want to find the angle between two vectors, you don't need to use any geometry at this point, right? You can simply apply the formula and then you can find the angle much faster this way. So let's do a quick example. Suppose U is of components 3, minus 1, and 5. V is of components minus 2, 4, and 3. And cosine of theta, U dot V is 3 minus 2 minus 1 times 4 plus 5 times 3 over the magnitude of U, which is 9, square root of 9 plus 1 plus 25 over square root of 9 plus 16 plus 9. In degrees, let's put the answer in degrees, right? So let's see, on the top here we have 5, right? So minus 6 minus 4 plus 15. All right, 10 minus 15. No, the other way around. 15 minus 10, which is 5, over square root of 35, square root of 29. Use a calculator and convince yourself that theta, which is now, take the inverse cosine, right, of this quantity, is approximately equal to 81 degrees. Normally we use radians as a default setting for the angles, but for now let's leave it in degrees. Remember, same mechanics works for planar vectors, right? So let's say, as another example, let's say you have a vector A bar, which is minus 3 and 5, B bar, which is 5 and 12. The cosine of the angle between them you should do it on your own ahead of me. Stop the video and then do it on your own and then check with me later. Minus 10 plus 60 over square root of 4 plus 25, and then square root of 25 plus 144, 25 plus 144, that gives me 169. That's actually 13, right? So it's 50 over 13 root 29. Again, taking the inverse cosine of that thing should give you approximately 45 degrees. All right, let's move on with other applications of the dot product. A very important consequence of this is a quick way of checking that two vectors are perpendicular. Another very important property to keep in mind. So let's move on to the second page. All right, so let's write down our formula one more time for the cosine between two vectors, cosine angle of between the two vectors. So notice that if the two vectors are perpendicular, right? So if the angle between them is 90 degrees, cosine of 90 degrees is going to be 0. So if the left side is 0, automatically that implies u dot v is equal to 0. All right, so that means we can have a quick way of checking that two vectors are perpendicular, right? So we can write this as a default or as a secondary property, if you want, or additional property. Two vectors u and v are perpendicular, or another name for it is orthogonal, if u dot v is equal to 0. All right, so whenever you have the dot product equal to 0, you know that the angle between them is 90 degrees. So that means, and that's very useful to remember in computation. So for example, if we end up, for instance, manipulating a vector in terms of the standard basis, so remember, standard bases are those unit vectors in the directions of x, y, and z. So now we have some properties related to those vectors, right? So remember, I stands for 1, 0, 0, j for 0, 1, 0, and then k for 0, 0, 1. Now with the operations we have already established, so first of all, these are unit vectors, their magnitude is 1. Any two of them are orthogonal, because obviously the angle between them is 90 degrees. You can check immediately that the dot product between any two of them is equal to 0. Here's another application of this. Sometimes, for instance, you may want to figure out, let's say you have a vector and you want to figure out another one, or you want to figure out a certain component that makes another vector perpendicular to a given one. So a typical application, you have some of this in the homework as well. Let's say I want to find some coordinate x such that the vectors minus 2, 1, 1 and the vector x0 minus 2 are perpendicular. So that means you need to find x such that the dot product between them is equal to 0, according to the property I just mentioned. And so that makes, this gives you a simple equation then in x, minus 2x plus 1 times 0 plus 1 times minus 2 equals 0. And that means x is equal to minus 1. So finally, the last topic for today, which is another direct application of the dot product, is the so-called scalar and vector projections. A very important application, and I'm gonna add actually a little video with some quick examples from aviation when this concept actually plays a role. I mean, it's not just in aviation, lots of other examples you can imagine. But let's see what the question is all about. I mean, before we describe the tool called a scalar and vector projection. So suppose, for example, that you have a vector v, and let's say that indicates, I don't know, velocity, for example, or some other physical quantity. And there is another force acting on the object, but at an angle corresponding to the path of that object, right? So let's say this is a force here that acts on, let's say, let me make it, yeah, let's say v is over here, like that. And then F is here, acting on the object at an angle theta. So notice that you may want to know how much of the magnitude of F actually is in the direction of the motion. There you can ask lots of questions, but roughly speaking, in words, the whole point of projection, the scalar projection at least, right? So for the scalar projection, you want to figure out how much of the magnitude of F is in the direction of V. Why we want to do that? Again, lots of applications. Maybe I'll show you with a additional video at the end. But in the case of motion, for example, let's say, for instance, F is the let's say is the wind, right? So then you want to know how much of the wind force actually helps the movement of the object, if any. Does it help? Is there any component in the direction of motion? Is it against it? And so on and so forth. Geometrically, you want to know essentially the length of this piece here. I mean, it's as simple as that, right? I mean, you want to know the length of that projection, right? You take the vector F, you project it onto another vector V, which may have whatever other length, and then you want to figure out the length of that side, right? Which is obtained by projecting the terminal point of F onto V. So just like before, when I showed you how the cosine of theta is derived, we're going to use geometry, but with the vector notation and operations, so we can have a much more efficient way to measure this projection. So there's nothing really fancy at this point, actually. How do you compute this length? Well, we just basically use a trigonometric function. Notice that the projection is going to be the adjacent side of theta. So this projection, this scalar projection, which by the way is denoted by the component, using the notation in our textbook at least, the component of the force F onto V. So you read this as component of F onto V. So to keep with the notation or the language in the book we use, the index vector here is the vector onto which you project the other vector F. And how do you compute it? Well, let's actually change back to the dark color here. We simply state what the cosine of theta means in that triangle, right? So that component, because it's the adjacent side of theta, is going to be equal to the hypotenuse, which is the magnitude of F, times cosine of theta, right? So the cosine of theta is going to be the adjacent side, which is the actual projection that we want to compute, times cosine of theta. But now we have a formula for the cosine of theta that we obtained previously. Look back on the top corner here. So now cosine of theta can be written as f dot v over the magnitude of f times the magnitude of v. And the magnitude of f cancels. So now we have this quick formula. Let's write it here in red. That the component, the scalar projection, the component of the force or the vector f onto v is f dot v over the magnitude of v. So I'm going to actually write it on the second page as well, and then we can go over some examples. Now, before we move on to the second page, remember this is a scalar. The component, the scalar projection, or the component, as the name implies, is a real number. F dot v is a real number divided by the magnitude of v, which is also a real number. All right, so stay tuned for the second page. For the next page. All right, so let's actually do the picture one more time here. So I can have it. So the length of these, is going to be the component of f onto v, which is f dot v over the magnitude of v. So let's actually do an example later on. So that's the scalar projection, because I also want to do the vector projection. So this is the magnitude of the projection vector. What if I want the actual projection as a vector? Okay, so what if in the computation we want this guy, this vector? Let's actually emphasize it in the red color here. Right, because so far this component of f onto v is just the magnitude of that vector. So I want to go slowly a little bit on how you obtain this, just for practice, to understand how these operations work, because there is kind of like a standard procedure if you think about it. And this is basically one of the values of that technique of normalization of a vector when you create a unit vector from a given one. So the mechanics is like that. I know the length of the vector that I want to produce. I just computed here, right? That's the component of f onto v. But now I want a vector of the length of the projection, right? Of that, with that magnitude. So, and I want that to be in the direction of v. V has a different length, right? It's up until here, not it's different than the length of the projection itself. So the first step is normalizing v, so that I can basically take only the direction of v. Normalizing means that creating a unit vector in the direction of v. Remember, you achieve this by scalar multiplying the vector v with 1 over its magnitude. So by dividing, if you want to use an abuse of language, because we don't have division of vectors, right? So when I say divide of v when I say divide v by the magnitude of v, that's an abuse of language. I really mean scalar multiplication of v with 1 over the magnitude of v. But the length of this is going to be 1, right? So this will have magnitude 1. And then I want to make it of magnitude equal to the projection. But the length of the projection is going to be the component of v f onto v. Okay, so the vector, the projection of f onto v as a vector, which is denoted, again to use the notation in our textbook, by the shortcut projection, right? Projection of f onto v is going to be the scalar that represents the length of that projection, scalar multiple by the vector, by the unit vector in the direction of v. And so, of course, we can simplify this a little bit, and let's come up with the actual formula for the projection of f onto v. We can combine the scalar. Remember, if you look carefully here, this is the scalar, this is a scalar, and remember we can associate a scalar together into one big parenthesis, f dot v, and so v, magnitude of v by itself, that's going to be the magnitude of v to the power 2, scalar multiple with v. All right, so let's keep this side by side, and don't forget that altogether the relationship between them is that the magnitude of the projection is nothing but the component of that projection, the length of that projection. All right, so let's do an example. Suppose that I have a vector. It's also important to get used to various notation for these vectors. I used f and v, but various problems will use various notations. So let's say I have the vector u given by 151, vector v given by 151, and then the vector u given by 212. We don't need to sketch anything again, and let's say I want to figure out the component of u onto v and the projection of u onto v. All right, so let's start with the component. Make sure you be carefully write down the denominator correctly, right? So if you look at the formula over here, the bottom is the vector onto which you make the projection. So on the top is u dot v. Right, so we're going to have a dot product 1 times 2 plus 5 times 1 plus 1 times 2 over the magnitude of v, which is 1 plus 25 plus 1. That gives me 5 plus 4, which is 9, over square root of 27. I can simplify that a little bit. Can I simplify it nicely or not? So I can root 27, that's 3 square root of 3. Yeah, I mean, this simplifies to square root of 3. So that is the magnitude of the projection, right? So if you were to, I mean, I said I didn't sketch them, but let's say this is u, this is v. All I did so far, I found the length of the projection vector over here. And now the projection, in other words, the actual projection as a vector, according to the formula, that's going to be u dot v over the magnitude of v squared, scalar multiple with v. Now, I already computed the dot product before. On the top here, that's 9. On the bottom is the magnitude squared, and this is scalar multiple with the vector v, which is 151. 9 over 27 is 1/3, simplifies to 1/3. You can keep the scalar out, or you can bring it inside, and this is the actual vector. And you don't need to, but to convince yourself that the length of the projection is the actual component, let's do the length of what we just got here. 1 over 9, 25 over 9, 1 over 9. That gives me root 27 over 9, which, as expected, is square root of 3, which is exactly the component. So I think that's enough for today. I mean, I think I'm gonna add a little presentation video, nothing to compute, but just to, I always like to illustrate the whole concept of projection and how important it is in applications like aviation, to show you how the trajectory of various airliners look like for long trips, and how they actually take into account the direction of winds. So basically they have sophisticated, obvious algorithms to make the flight as efficient as possible, in the sense that take advantage if the component of the wind helps the motion, is in the direction of motion, or minimize the damage if the wind is actually against the direction of motion. It's far more complicated than just that, but I think it's gonna be a nice discussion to have at the end of this lesson. So with that, I'll see you next time.